We've been looking at power functions. Here are a few of my favorites.
I love power functions.
I hate to pick favorites, but here are a few anyway.
All right, good.
How you doing, Ms. Stewart?
I'm great. How are you,
Good.
Mr. Haas?
So, in the context of power functions, we're going to talk about some of this vocabulary. Or maybe I should say it the other way around. So we're going to talk about this vocabulary in the context of power functions.
Right.
This is the kind of vocabulary that's going to come up again to help us describe other functions. But we're going to talk about in terms of power functions. You've seen this before, I'm sure. So perhaps we'll talk about increasing and decreasing. First, I'll just go right down the list. How does that sound?
I think that sounds great.
So functions which are increasing or decreasing are just functions that have, or portions of the function, I should say, that have either a positive slope. Positive slope means increasing. Negative slope is decreasing. So if I were to walk along this function, at this point, here I am walking down the function. You see what's going on?
I do.
Right.
So you're walking from left to right on the x-axis.
Yes, that's right.
Okay.
So I'm going downhill here, so I would say this portion of the function is decreasing. And of course, right here, I'm standing on flat ground for just a moment.
Right.
And then I start walking uphill. Well, that portion of the function is increasing. So that's all this means.
Good.
Right? Negative slope decreasing, positive slope increasing. So how about this function?
I'm thinking if I'm walking from left to right, the function is increasing.
That's right. So I'm increasing, I would say, for x values less than 0, right, on this side, and I'm decreasing.
And then, I hit a vertical asymptote there.
Oh, right.
Where the function doesn't exist.
Thank you.
And then the function is decreasing for all values x greater than 0.
That's exactly right. And just looking at, how about this one?
Ooh, that's interesting. So function is increasing and then still increasing.
Sure. So this one would be increasing for its entire domain.
Its entire domain.
And actually, this would be increasing for its entire domain as well. It doesn't exist for negative x values, but for its entire domain, it is in fact increasing. We're going uphill the whole time. Don't get this mixed up with a slope that's increasing.
Ah, yeah, that's right.
More about that later.
Later. We're talking about a function increasing or a function decreasing. Yeah.
This one, in fact, is increasing, although the slope is decreasing. But more about that later.
Confusing.
Okay.
All right.
Let's talk about concavity a little bit. Concave up functions. Concavity is either described as concave up or concave down. Concave up functions look like a U, or some portion of a U.
Like a bowl.
Yes.
Or a satellite dish.
A bowl. Do people get satellite dishes anymore?
I don't know.
Maybe I don't know.
Maybe they don't.
And a concave down function looks like a bowl that's flipped over, or a satellite dish that's fallen off.
Or an umbrella.
Or a what?
An umbrella.
An umbrella. Right. That's not the other way around.
That's right.
An upside down, a right side up umbrella.
Okay.
Yeah, all right. Anyway, so if you can match up, sometimes this confuses students.
It is, yeah.
If you can match up your function with something that looks like a U, or part of your function, that portion is concave up. So I mean, this first one is pretty obvious.
Yeah.
This is concave up the whole time.
The whole thing is like a big U.
This is my U.
Concave up.
Can you see what's going on there?
I'm seeing what's going on.
So if I move it over here, well, this is also a concave up piece. Right now I don't have the other part, but this piece is concave up. I can match it up with part of my U.
Yeah, see, that's where the satellite dish comes in because it's slanted a little bit.
Thanks, Mr.
Okay.
So this is also concave up, I would say. So this guy's concave up the entire time.
Okay, so I would say that function is concave up for its whole domain. Both of those top functions are concave up.
I would say that as well.
Good.
Right. This guy, concave up on this side, but notice there's no way for me to match up any portion of my U here, so this piece must in fact be a concave down piece right here, and I think that's kind of obvious.
Yeah, so it's concave down, the function's concave down for all x less than 0.
Right.
And this function is concave up for all x greater than 0.
That's exactly right.
Concave down, concave up. I'm getting it, Mr. Haas.
Thanks. But again, there's no way for me to match up my U here on this side, so this is a concave down piece.
So that function is concave down for its whole domain.
All right. More on this later, but concavity is actually what's happening to the slope.
Right.
I mean, a concave up piece means the slope is increasing, actually.
Yeah.
Concave down piece means the slope is
Decreasing. Ooh, tricky.
More about that later when we get to the calculus part. You'll see where we're going with that.
Very nice.
Next, I'm going to talk about domain and range, and we've talked about this before. Functions. Some of these functions have a domain of all reals. Some of these don't exist at various points, like 0, for example, with these particular power functions. So, domain of all reals just means I can walk from one end to the other, and the function is continuous. There's no breaks or asymptotes or little holes in it. So of course this guy has a domain of all reals. This guy does not. In fact, there is an asymptote here. The function does not exist when x equals 0, and you can see if I fill in a 0, it makes the denominator 0. And you know, sometimes this bothers students, and this is a power function. I could actually rewrite this as y equals x to the negative 2. So there's my x, and there's the power is negative 2. That really means it's in the denominator. You know how that works, Ms. Stewart.
Yes, I
right?
do.
Yeah, okay.
So that is a restricted domain. All reals except x cannot equal 0.
All reals, x does not equal 0.
Wow, that looks like a domain of all reals to me.
All reals,
Every
right,
x
it's
has a
continuous.
y.
I can walk from negative infinity all the way to positive infinity, right, in terms of my x values.
Very nice.
Yeah.
Yeah, x, the domain is just x greater than or equal to 0.
That's right.
Because that little 1/2 we have to remember is another way of thinking. So square root is the other.
Right, and you know you're not allowed
notation.
to have a negative in the square root. Well, you've got imaginary numbers, and we dealt with that last year. But these are if you have a negative under a radical, under a square root radical, it's going to be a non-real. So the domain is only positive values greater than 0.
Very
In this
nice.
particular case, range, of course, is y values.
Okay.
So I could just look at, I'm looking at my function in the y direction.
Yeah, in
Can I
vertical fashion.
Say that?
Yes, you
Y-
can.
Okay.
You
So,
just did.
yeah, well, anyway. So the y values of this guy, as you can see, nothing lives downstairs here. The range of this is y values greater than or equal to 0.
Yep.
This is pretty obvious
This is
stuff.
pretty
You've seen
clear,
this
I
before.
think, yeah. Y is greater than 0.
Notice it just never hits 0 here.
And that's, of course, because you can't divide 1 by anything and get 0
That's right.
as an output.
That's exactly right.
Yeah.
Exactly right.
That range would be all reals.
All reals goes
Every
up and
y
down forever,
gets
and
to
of course,
So all y's greater than or equal to 0 would be the range for that
Right.
square root.
should I go for it? Just do end behavior.
Let's
real
just
quick?
go
All
for
right,
it.
all right.
You're doing great. You're on a roll.
Yeah, thanks. All right, so real quick, end behavior. This is also a little confusing. This is what happens to the function when x goes to infinity. I'm pointing to infinity.
You are.
So I'm not pointing at
It's
anyone.
way off to the right.
It is. Or when x goes to
Negative infinity.
negative infinity. I'm
Pointing to the
in
left.
Negative infinity.
I'm looking at it.
Do you see how that?
Yep.
Do you see anyone out there?
No,
All right.
no.
So I'm talking about what happens to the y value when x goes to infinity.
Because when we talk about a function, what does the function do? We're really talking about what is the y value doing.
That's right. F
Yeah.
of x is the same thing as a y value.
Good.
So I'm just going to actually write this one, if you don't
I
mind.
think you should.
Okay,
Because the
so when-
notation's a little tricky.
Yeah. So when x goes to negative infinity, you see that one, love?
Yeah, I do.
X is going to negative infinity. I'm trying to go in this direction forever and ever and ever. My function value, my y value, is going up forever and ever and ever. I would say y is going to positive infinity.
Yeah.
And you can see that it's also going, when I go in the positive direction, it's also going up forever. So I'm going to say when x goes to positive infinity, y is also going to positive infinity.
And that's the end behavior.
That is the end behavior. And this is how you would see it written typically.
Yeah. Very good.
This guy, this messes students up a little bit also.
So
X, I'm trying to go in this direction.
going towards negative infinity. So the x is heading towards negative infinity. Now let's see what the y is doing. The y looks like if you put your finger along the function, it's approaching 0.
I'm approaching 0. I'm approaching the x-axis, which
Yeah.
is the y value 0.
Yeah,
Yeah.
that makes sense.
All right?
So now as x approaches positive infinity, that means I'm walking to the right You know, where X is a million, a billion, a Google. Yeah, the Y is approaching zero
And,
there too.
You know, I hate that. I don't want you to have to memorize this stuff. This should make sense. If you look at the function, look what's happening. If I put in bigger x's, 10, 100, 1,000, 1 divided by 1,000 squared, well, that's puny. It's almost zero.
Almost zero.
Notice I can never get to zero, and you pointed this out before, I think. If I can never get to zero, no matter how big a number I put in here, it's always going to be, you know, a tiny, 1 billionth, 1 trillionth. That's pretty close
Point
to
zero
zero.
zero 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 zero
Pretty
one.
close, but it's never
Basically
gonna be-
zero.
We could say basically zero.
Infinitely close to zero.
Okay, this is another one where as I go in the negative direction, I'm going towards infinity, but this time negative infinity. So I'm just going to do this real quick.
So-
X goes to, and you've seen this arrow notation before, I think.
Yeah.
When X goes to negative infinity, my function value,
Your Y value.
my Y value, is also going to negative infinity.
Good.
Negative, that's an arrow, by the way, negative infinity. When X goes to positive infinity, going in this direction, my Y value is going up
To positive infinity.
to positive infinity, and
And
this
this
last
guy,
one, well, it's not.
there's no, X is not approaching negative infinity because it's now part of the domain.
I'm only worried about the positive direction. So X is going to positive infinity,
Y is
Y.
just going up, 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 up.
also to positive.
Yeah. That's beautiful,
So
Mr.
that's a
Haas.
quick review in terms of increasing, decreasing, concavity, domain range, and end behavior of these power functions. You're going to see these terms again.
Thank you.